Yes. So today's workshop is actually the official release of EMUX. I've been working on EMUX for 4 years, 4.5 or something years. It used to be called ARMX once I started, when I was originally working on it. And now the name changes for a very specific reason. My name is Saumil Shah. You folks know me already. Let's go right to the heart of the matter. So the reason why we call it EMUX now is it's moving more towards a general purpose IoT device emulation framework. I finally got off my lazy ass and integrated MIPS support into ARMX. I mean, ARMX was quite well polished and well oiled. I made a lot of headway into it. Whenever you're emulating an architecture, like there's a whole lot of peripheral things that you need to get your hands dirty with. You need to learn a little bit about the inside tricks, strange compiler errors, makefile issues, cross-compiler stuff. And over the period of months, you'd spend browsing Stack Overflow or Linux kernel mailing lists or mucking around with kernel configurations. You learn, one little pearl, one little gem of information every now and then. And it is all that information that you distill together and automate it. That's what makes an emulation framework. At least that's what I feel. I did that with ARMX. I spent about 4 years smoothing out all the little kinks and rough edges that ARM emulation was facing. Got it working to quite a satisfactory level. And now I feel that we've come back full circle. When I started with MIPS, I thought like, oh, this is going to be easy. And then I catch myself with the same famous last words like, yeah, right, whatever. It's easy until it's not. When you start peeling off the layers, you realize that a new architecture means there's an entirely new set of quirks that it brings. MIPS has been around for a very, very long time. In fact, MIPS devices are more popular than ARM devices in the IoT world. Like you could pick up like a cheap D-Link router for like $5 or $10, depends if it's used, it's cheaper. And these MIPS devices are everywhere. Right? When you're trying to emulate a MIPS device, you suddenly realize that MIPS is just not MIPS. It's not a single architecture by itself. There's several versions of the CPU. And you also have different endianness. So there's a sizable percentage of devices which operate in big endian mode, and an equally sizable percentage that operate in little endian mode, which means you're now literally having to deal with 2 CPUs. It's the same CPU, but MIPS in big endian and MIPS in little endian. So I ended up overhauling the architecture of ARMX. Fortunately, so a lot of it is essentially shell scripts. So not too much of surgery required. But finally made it work, and this is the release. The website is emux.exploitlab.net. The instructions that I pasted on Discord are ripped off from the website itself. So even later you want to play with it, you can use this. You can use this recording and follow along at a later stage as well, and just go through the instructions. I will be publishing updates to the Git repository rather regularly. I will sometimes even tweet about it. So if you want the latest and greatest, go to GitHub and smash that like button. What is EMUX? Let's get into it. We're going to start this discussion with a little case study, right? We have an IoT device, and what I thought I'm going to do in this workshop is we will take an IoT device. Here it is, this IP camera. This one is an ARM IP camera. And the reason I take this is because I've tried and tested this. This demo works, and I don't want to screw up the demo now. We'll take this, we'll extract the firmware from the chip itself, And then we'll see how to analyze the firmware, plug that firmware into EMUX, and get an emulated instance of this IP camera running on EMUX for us to play with. So I thought that would make for a good demo. Along the way, we will study how the various files and folders in EMUX come together. And how do you go about creating your own device? This is a rather simple one. There are some more write-ups about emulating complex devices that I've posted on the GitHub as well. More on that later. When we look at IoT devices, what are they? Essentially, inside, they're nothing but specialized computers. This IP camera is running Linux. It's running Linux on an ARM v5 CPU. It is a rather old ARM CPU. It's around 2007 or something time frame. And this CPU is implemented as a system on chip and SoC. So you don't have too many discrete components all into one single package. There's two fundamental differences between IoT devices and regular desktop computers. While it's the same Linux that runs on your desktop versus the Linux that runs on the IoT device, the organization of the peripherals in the IoT device, the storage, are vastly different. And as a result, we have a slightly different boot up process than what we're used to seeing on a regular desktop computer. If we want to emulate a device, the first thing we need to know is familiarize ourselves with the boot up process and the way the firmware is organized on the device. I'll give you a quick tour of the boot up process. Everything in all the storage in the IP camera resides in flash memory. Most likely it is NAND flash. These days also you have devices with NOR flash. The fundamental difference between flash memory and a spinning disk or block storage that you have on a desktop is flash memory cannot be easily written to. It can be flashed, which means that an entire block is erased and a new unused block is overwritten. Imagine flash memory like a CD-ROM with extra tracks available. So you write the full capacity and then you want to write some more. You used to get these CDRWs, right? CD read write, but it's not really read write. You nullify or you cancel the earlier tracks and write some more. But once the entire capacity is used up, you cannot write to it anymore. So that's pretty much the way flash is organized. All your software is stored on the flash. You have the bootloader, you have the kernel, you have the compressed file system. All of this forms the firmware, and that is stored on the flash. When you boot up the CPU, the power on control goes to a specific area of the flash memory where the bootloader is present. The bootloader will scan the flash memory for other partitions, find where the kernel is, find the kernel partition, and then it will hand over control to the kernel. The kernel in turn will start loading up various drivers and things in the memory. It will find where the root file system lives in the flash partitions, and it will mount the root file system in the memory. This is where the first fundamental difference is between a disk and a device. You have the file system on disk. The kernel simply mounts the file system as it appears on the disk, and you're interacting with blocks on the disk. With IoT, the flash memory, you cannot write to it. So what do? You take the file system and mount it as a RAM disk the file system can be only written to when it is in the RAM. If you power off the device, the file system goes. When you power it on, it has to rebuild and mount the file system all over again. When you're storing the file system, like if you look at regular block disk, you have inodes, you have blocks, you have metadata, you have directories and things like this. File systems take up a lot of space. We don't have a lot of space in the device. So your space is at a premium. Instead of your regular file system like ext2 or ext3 or heaven forbid riser fs, things are stored in a compressed format. Most typical file systems that you find on embedded devices are CRAMFS, SquashFS, or now you have JFFS2 as well. All of these have a property that they will be uncompressed and mounted in the RAM disk. Once your file systems are mounted, that's typically, your file systems are mounted, your network drivers and all the stuff is loaded from the kernel. You will then pass control from the kernel to the user land. So the user land will kick off your init process, and the init process will read init tab, standard Unix boot at this point of time, but everything is happening from the RAM disk. Whenever you're setting up your computer, like imagine you got a new computer and you just installed Ubuntu on it. Now you want to configure it, you want to set your own usernames, passwords, you want to configure the IP addresses and the Ethernet gateways and all that. You want these configurations to persist. On disk, it's easy. You just edit the password of the shadow file, you edit the network configuration stuff, and it's good. It just lives there forever. In an IoT device, persistence is achieved by something called the NVRAM, the non-volatile RAM. And all your configuration parameters will be saved in this writable, flashable area of NVRAM. And the init scripts will essentially pick up the parameters saved in NVRAM and rebuild all the configuration files on the fly. So whenever you boot up an IoT router or something, you'll see like the light keeps on blinking until it enables. The boot time is rather long. What's happening is the init scripts are a bunch of very poorly written scripts. They'll do some ugly parsing, and they will create all these configuration files on the fly in a temporary directory in the RAM disk. And then they will start kicking off the various services. Your system services will start first, and your custom applications will start thereafter on top of it. So once all your final applications started, the boot up process is ready. We will go back to this boot up process once again when we're trying to emulate the IP camera. For emulation, what we fundamentally need is the firmware and the configuration. So I'm going to talk to you about how do we get a copy of the firmware, and then once we get a copy of the firmware, what do we do with it? Part one of this whole workshop is going to be extraction. That is going to be led by a demo. And what I'm going to do is, after I extract the firmware from the flash memory, I will post the copy of the firmware on Discord. You folks should be able to download it. And then we can start splicing the firmware in EMUX and emulating the IP camera on the fly. Okay. Right. Now, 3 ways of extracting firmware. The first way is you grab the firmware from the website. Like if you get the firmware, you download it and you grab the firmware. That's nice. It's easy. It's quick. It is the least invasive of all processes. But the problem is you may not get a complete running snapshot of the firmware. And by running snapshot, what I mean is the firmware is not just the file system or just the binaries, but I also want a snapshot of the configuration, the key value pairs that are stored in NVRAM. That you may not get because it's factory default. The next best thing to do is to extract this via a UART interface. You have a lot of tutorials on the web, how to open up IoT devices, find the unsoldered UART pins, and you can connect it to like a USB UART dongle, get a console, and more often than not, there's like a fully functional root shell hanging off on the serial console. You get a root prompt, and then you go in, you grab everything that you need using DD and things like this. There's a lot of stuff that discusses this, so I thought I'm not going to take that route. I'm going to take a slightly more difficult route. By the way, I'll show you this. Every time I buy an IoT device, the first thing I do is open it up. And then if you see, let me show you the screen. So if you see the router over here, this is a serial port. It doesn't come with a serial port. I opened it up and then I found the UART pins and I stick a serial connector. And then I have in my lab, I have like a serial wire that I just plug to it, and then I can get a serial console going. So it's a fun project to do. It's really, and then you can debug this device and do what you want to do with it. Makes it fun to work with. But we're not going to use that approach. What we're going to do instead is we will open up the IoT, the IP camera, and extract the firmware from the flash chip itself. If this is one of my, there's a photograph I took at 44Con where I demoed this in class, and one of my friends from British Telecom brought this EEPROM programmer, which was nice. You could clip onto the flash chip and then literally suck the firmware out of the flash. I'm going to do the next best thing over here. I'm going to give you a demo with a very, very inexpensive and a very powerful flash reader. And this is the Tigard. Before I proceed with Tigard, I want to give a hat tip to my dear friend Guvan Bairam, who is on the panel. Guvan and I have worked on EMUX for a long time. Guvan is the guy who tests out all my shitty code and essentially keeps me sane. And Guvan also taught me how to use the Tigard. The Tigard is a beautiful device. It is built by a dear friend of ours, Joe Fitzpatrick. Joe can basically build anything in electronics. The guy is a wizard. You wake him up and he can start talking pin numbers from sleep. The beauty about this device, it's an FT2232 device. There's a lot of FT2232 devices which can help you read flash memory. The Tigard works with SPI flash. It has a UART interface. It has I2C bus, and it also has JTAG connectors on it. The package is so beautifully designed. I mean, literally, Joe has taken care to number the pins for the SPI flash in the same order that you find on an 8-pin SOIC package. They are very well labeled. At the back of the Tigard, you get a cheat sheet with all the pins and the tables laid out. Very, very thoughtful. So if you're really beginning into playing around with I2C or you're playing around with SPI flash, highly recommend you pick up the Tigard and support a friend. It's a well-designed piece of hardware. Yeah. And as a hack tip, Guvan's Goven's Tiger is sleeping right now. So this and Goven likes Tiger for two reasons. Okay. So what have I got in this thing? I have actually got, I did not want to like break open the IP camera directly because it gets messy. So I have a bunch of flash chips. I'll hold this one close to the camera. What you see here is an SPI flash chip. It is an 8-pin package. And this is soldered to a breakout board. And these are the pins that we're going to wire up. It makes it easier to deal with than the clip. So I've actually cloned some of the firmware that I have on my IoT devices. I've cloned them in this little box of chips so that I can play with it at will and do firmware extraction demos without destroying my hardware. So that's what we have got plugged in the Tiger. This is the IP camera, 64 megabit, 8 megabytes IP camera flash, and we're going to extract this with the Tiger. So let's hope the first demo now works. Okay. If the demo fails, I'm going to just literally shout to Goven for help. Right. First, let me just check if the Tiger is plugged in. Yep, sanity check passes. The Tiger is plugged in. Reading from flash memory is now actually made. It's a rather easy process now. There's not much special stuff you need to do. You have an all-in-one workhorse program called FlashROM. And FlashROM is being maintained for a long time. It's being developed for a long time as well. So FlashROM works with a number of EEPROM and Flash programmers. So let's just actually saw notification flyby. No, so FlashROM works with a number of Flash programmers. What we're going to use is the FT2232 SPI, which is the chipset that Tiger implements. Another popular Flash programmer is this one. There's a lot of Chinese clones, the CH341A SPI. You get quite a few of those floating around. And a number of people have also used the Bus Pirate. It entirely depends upon what you're comfortable with, right? Eventually, it's like your favorite screwdriver. You have a couple of them and you always want to use those, even though other screwdrivers are exactly the same. These ones just feel nice in your hand and you work with them. So with Tiger, let's see how it is. I'm also going to post how I have wired up the flash chip. I'm going to post this info on Discord just for information's sake. And later on, it makes for easy reference for you folks. So this is how the flash chip looks like. Right? There's 8 pins. You have chip select, data out, write, protect, ground, data in, clock, hold, and VCC. And what I just pasted on Discord is the chip wiring diagram, how you wire these various pins in the Tiger. So yeah, this is how the Tiger board looks like. This is how the yeah, this is how the pins look like. You have JTAG, you have SPI, you have I2C, you have UART. And there's a cheat sheet, which is at the back, which tells you where each pin goes. On the IP camera, when you open the lid, this is the flash chip that you find on the board. And I've taken up a close-up view of the WinBond flash chip. And the same WinBond chip is replicated on the breakout board for this demo. Okay. So at the end of this extraction, what we're going to get a copy of the kernel, and we're going to get a copy of the compressed file system. And eventually what we're going to do after this is place the file system and the kernel in EMUX. Not directly, we'll have to do a little bit of modifications. And then we'll see how to boot up the emulated device with the extracted software. I'm going to take a couple of minutes. If there is any questions about anything you folks wish to ask on Discord, go ahead and do so. If you want to go on voice, we'll be happy to unmute you and bring you onto the voice chat, voice talk as well. Quick show of hands. I'm gonna post a message, and then I would like you folks to react to it. Okay, so the first message it's up on Discord. If you got Docker and EMUX downloaded, just react with a thumbs up. If there's problems, react with a thumbs down. We can try and go for some troubleshooting. No, don't worry about it. It's a Sunday workshop. There's only a few of us here, so hang out and make yourselves comfortable. All right. For those of you who are having problems, just post a screenshot of what's going wrong, and we'll get to it just after I finish the firmware extraction demo. Right. And maybe one of the other participants can help out as well. Let me now do the demo for the firmware extraction. Okay. Command is going to be okay. So here's the extraction command, and pretty much all your flash ROM commands are going to look like this. You specify the programmer. The -p is the programmer. It's This is the FT2232, which we use for Tiger, and Tiger has 2 ports. We're going to use port B. Now, this parameter divisor equals 8. It essentially slows down the flash timing. The slower it is, the more reliable. Of course, the slower it is, it's more time consuming. So sometimes you just have to find a sweet spot, what the frequency is, and usually a divisor of 4 or 8 does the job. I typically prefer a little slower one, so 8 is fine. And then once it does it, it's going to read everything into this blob called ipcam flash8m.bin. Keeping fingers crossed. Yep, it read it. Says found the Winborn chip, which is an 8 megabyte flash chip, reading flash, and then done. After it is done, the file is created, which is 8 megs in size. This is essentially, it's as simple as this. The challenge is, of course, getting the flash chip out and cloning it and all that stuff. Once you get this blob, this is your full 8 megabytes of flash memory. We're now going to work on how to parse it, how to find the various partitions that might be there in it, and then work on copying them over to EMUX. I'm going to post this binary on the Discord channel as well, and you all can download it and play along with the binary. Okay, so I posted the flash memory stuff on the Discord channel, and the message is pinned, so you could grab it and download it. There's another question. I'm just going to read it out from the channel. Do you need to power up the IoT to extract the firmware from the SPI flash? No, not really. And the reason I say no is when you power up the device, the CPU will possibly acquire a lock on the flash memory, and it'll be using it. So while the CPU is using it, you're not going to get a clean firmware extract, or sometimes you just might get a variety of zeros being read out. So my preference is always to leave the device unpowered. However, if you're trying to read memory which is soldered onto the device, even if you clip with the SOIC clip, the flash programmer will be powered, and there will be voltage provided on the VCC pin. Now, if this happens, the chip has to be powered up for the memory to be read, but the chip's voltage is also connected to the overall voltage rail. So what happens is the CPU sometimes gets powered up, and then it locks the chip again. We would know that better if we had a proper logic analyzer and on the traces, but I am not as skilled. Guven could answer that better. But the preference, I'm told, is you want to use a hot air gun and literally extract the chip off the board and then place it in the reader, read it, and then solder it back on, or melt the solder and place it back onto the board. And be careful not to screw up your device while you're placing it back on. Okay. I'm going to very quickly, I know there's a couple of confusions with some Docker installs. I'm going to very quickly try it out on my VM as well. This is a fresh VM. It does not have EMUX installed. So I'm going to follow exactly the same instructions and get it going. This is git clone works. It's a bit of a heavy repository because there's a few sample firmwares already provided in the repository to play with, and bulk of the space is just occupied by the firmware blobs. Also, with this repository, I have included a brand new MIPS CTF challenge. The challenge was released a couple of weeks earlier by Excel. She runs a CTF called Phone in the south of France. So this CTF first appeared at Phone, and now it's okay for general release. So if you folks feel like getting your MIPS exploitation skills sharpened up, I'll show you that CTF challenge, and you can work on it and do a nice write-up or something, brag about it. Okay, the Git repository for me is cloned. So now I'm going to go and build the Docker volume first, and then I'm going to build the Docker container. First, we just want to run, and I'm not running this as root because I've configured Docker to also run along with with regular users. Folks, if you have installed Docker afresh for Ubuntu, it's not going to work as is. Ubuntu and Docker are not the best marriage. You'll have to do some tweaking. A lot of people have faced problems with installing Docker on Ubuntu. There are C groups problems, and there are some permission problems and whatnot. So you'll have to probably do a little bit of care and feeding for that before you get Docker happily running on Ubuntu. First, I'm going to do build EMUX volume. Praise be Harambe. That's the name of the volume. Harambe must be praised. And once the volume is ready, yeah, we have Harambe. We then going to do a build EMUX Docker. Build for me because everything was in the cache. But if not, it's going to take a little while until everything builds up. So I have EMUX as an image, and let me now try and run it. To typically run EMUX, you're always going to need two windows. I also want to welcome my friend Noah for joining the workshops. Noah has also been helping out a lot with testing EMUX. Once your image is built, all you do is run EMUX Docker. And hopefully all goes well. You get it to run. I'm going to explain a little bit of the EMUX architecture here, and then we'll move to the second part of the workshop. We're close to the halfway mark, so we'll move to the second part of the workshop, is to emulate the extracted firmware. Now, if you look inside EMUX, there is one main directory which has everything, and that's the EMUX directory. So it's /EMUX. Everything you need is in here. Just for convention's sake, all the devices that I emulate, I name them with capital letters. So the AC15 is a Tenda router. I love me Tenda. The Archer C9 is a TP-Link router. These DV, this is a damn vulnerable ARM router, a damn vulnerable MIPS router, big endian, and a damn vulnerable MIPS little endian router. These are mini CTF challenges that I'd created in the past. The phone CTF is the latest CTF challenge, and the TriVision IP camera is the one that we're actually emulating right here, but an emulated instance is already provided. And all these other files, the debug logs and the devices, host FS, QEMU options, these are all parts of some shell scripts and some build root images which we need for running EMUX. Everything goes in the EMUX directory. There's also a workspace directory. Now, this workspace directory is mapped with your host file system. So anything you put in the workspace from your host, you get to see it in Docker. And anything you want to put back to the host, you can see. So it's a bind mount, which is shared between the two systems. So that's how the organization is. So what I'm going to do now is I'm going to grab that IP camera binary. I'm going to place that IP camera binary in the workspace, and then we will use EMUX. We'll use binwalk and all the tools in EMUX to extract and then eventually emulate the IP camera. I'm going to now switch over to my regular instance of EMUX, not this Ubuntu instance. So once again, what we're going to do is, I showed you this is the flash chip. This is how you wire it up with the Tigard. This is the flash chip on the actual device. And what we're now going to grab from the flash chip is this is the file system and the kernel. To emulate this, right, we need to do several things. So first, we're going to use QEMU. We're going to use QEMU to emulate the CPU. There are 3 QEMU binaries that are provided in EMUX. There's a QEMU ARM binary, and there's QEMU MIPS little endian and MIPS big endian binaries. So they could be used to emulate any of the devices. We will be able to extract the kernel from the flash chip, but unfortunately, we cannot use the extracted kernel in QEMU. Now, the reason is the device's hardware does not always match the example hardware that is provided by QEMU. The QEMU is highly customizable, right? It's you can define your own hardware boards in QEMU. If you're like a low-level machine wizard, you could implement your own board with it. I am not that wizard. I have very little knowledge. The only thing I could do was like add custom NAND flash to an existing board, but I'm learning. Like QEMU is kind of hard to learn because you have to RTFM the whole thing all the time. Therefore, what we're going to use in QEMU, we're going to use the example boards that are provided. In ARM, you have the V Express, the versatile Express boards, and the versatile Proto boards. In MIPS, you have a board called Malta. The hardware that is implemented on the V Express and the Malta boards is not the same as the hardware you'll find in the IoT device. And therefore, if you were to use the kernel extracted from the firmware, the kernel is not going to be able to detect the correct hardware. Either the kernel will panic and hang, or the kernel will just freeze, or it will you simply get nothing going on. It might be just spinning. What we will therefore do is, from the extracted hardware, from the extracted flash, we will only use the file system. We will take some hints about the kernel, like what kernel version it is, and possibly try to fingerprint the kernel and identify the kernel configurations. But we will eventually have to compile our own kernel and then use it. So how do we compile our own kernel? Well, for those of you who compiled Linux kernels, you know how challenging the process is. You'll have to look at all the various menu config options and click this, click that. Be ready when you're emulating a new device, be ready to spend hours of compiling and recompiling and recompiling and recompiling the kernel. You miss out one parameter, you'll have to do it again. There's a little bit of a cheat sheet that I've gathered, but it is still like, it's more of an art and not a science at this point. You have to go a little bit by experience and a little bit by luck. It's the truth for building custom kernels. And to make matters even more interesting, it's not just a custom kernel, it is a custom kernel using a cross-compiling environment, which, because why not? Unless you have a very fast Raspberry Pi, you could build a native ARM kernel on. I build all my kernels on an x64 Intel box using cross-compiler tools supplied by Buildroot. It takes a while getting used to cross-compiler tools. Once your environment is working, it's all good. Now, I have also created a repository. If you wish to get your own cross-compiler tools, and generate your Buildroot images, I have posted something on my GitHub, which I can pull up and show you. That will get a little bit of the pain eased up. Yeah, here it is. So if you go to my GitHub, you will see this repository called EMUX Buildroot toolchains. So these are pre-compiled toolchains for ARM and MIPS. These are essentially Buildroot builds everything. Buildroot will build you a full embedded system, ready to flash firmware. A beautiful system. It's a fantastic framework. The first thing Buildroot builds is the cross-compiler toolchain, and then it builds everything using the cross-compiler toolchain. So what I did is I extracted just the toolchains out of Buildroot and placed them over here. And there's some instructions also. If you want to build your own, then this is how you do it, and grab the toolchain from the user directory. But all you have to do is just literally grab these three XZ files, and you've got a good cross-compiler toolchain going. Hey, thanks. I'm going to pin this as well for you folks. There you are. Okay. Praise across compilers, and of course, praise be Harambe. IPCam firmware image. What do we have in those 8 megs? Here's the spoiler. We're going to see this with binwalk, but let me give you a visual view. So from 0 to 8 megs, you have the kernel. The orange block on the top is essentially a kernel. Now there's two, sorry, there's 2 parts in the kernel. The kernel, the first part is the uncompressed kernel, which essentially runs and uncompresses the second part of the kernel, which exists as a gzip stream. So both these orange blocks make up the kernel. Then you have the CRAMFS root file system, and then you have the tar archive, which essentially contains a few configuration scripts. So this is the firmware we're looking at, and I'll give you an overview of Docker of EMUX just after we've finished extracting the or parsing the firmware. Okay. I will now go to my Is everybody able to see my screen clearly? If you can read the text, react with a thumbs up, please. Super. Okay. In the second window, I usually always have 2 windows, 2 terminals laid side by side. The first terminal, I did a run EMUX Docker, which got me this. The second terminal, I'm going to attach another shell to the environment. So there's a shortcut called EMUX Docker shell, and I'm going to run that. So I have my 2 views side by side. I'm going to stick with the primary window first. I've placed the extracted binary in the workspace directory. Yes, to answer your question, are you running EMUX on Mac OS? Yeah, it's Docker on the Mac, and then this is running inside Docker. Yes, yes, I am. So, and I've heard reports. This has also worked for one of our TAs at Ring Zero when I was teaching the class in August. This has worked also on Docker running under WSL, Windows Subsystem for Linux 2 as well. So she was able to get it going. The only challenge was the ASCII art was failing, but everything else was working. So, okay, so I have placed that extracted file in the workspace directory. On the host, right? On the host, you have in EMUX, you have a workspace directory. You simply place that binary file in the workspace from your host, and then it'll appear inside the Docker environment as well. I also have some other stuff that is floating around from my R&D. We're not going to deal with that. I'm going to copy this ipcam flash atm.bin. I'm going to copy it in the temp directory, and then I'm going to run binwalk. Let's type the instructions over here. Let me just check if binwalk is good. Yep, binwalk is installed and running. Now I'm going to extract this using binwalk. Look at my cheat sheet real quick. And the command is, I'm going to paste the command in here as well. I'm going to pin it. There's a very good question on Discord. Is there a reason for running binwalk as root? For me, I mean, what the hell? Just run everything as root, right? What does it matter? This whole privilege separation is all bullshit anyways. No, jokes apart. Yes, there is a reason for running this as root. The reason is whenever you're extracting a file system, you want all the files to be preserved with the original attributes. You also want symlinks to be preserved. And you also want device trees, like special devices, MK not devices. You want them preserved as well. If you're not root, then these things will silently fail when extracting, and you will end up with a partial extract. And you won't know that, oh shit, these things are missing. You think like the extract went through well, and I should have everything, but just a few things are missing. So whenever you're playing around with file systems, extracting or modifying them, always be root. In an IoT device, anyways, it's root or nothing. It's like there's no real user. So get used to running everything as root anyways. You should see binwalk showing you the various binwalk will show you the various partitions in the flash. The diagram that I showed you is essentially what we're seeing over here. So these two blocks are the kernel. Then here you have the CRAMFS file system. And then there's this little POSIX star archive. Let's see what we got in here, right? Now, whenever you've extracted stuff, you'll get a new directory created, which always starts with an underscore. It's like underscore ipcam flash atem.bin. Inside this underscore ipcam flash atem.bin, you have all the extracted stuff placed in. So binwalk performs two passes of extraction. The first pass, it just cuts the blobs at various boundaries. How does it detect the boundaries? binwalk has a number of signatures, prefixes, various super blocks, kernel headers, file headers, binary headers. It can detect where a partition may end and a new partition may begin, and uses those heuristics to make the divisions. Once it has extracted these things, it will further try to see if it can fingerprint those blocks. For example, it automatically fingerprinted this third block, third partition, it got fingerprinted as a CRAMFS. And if it has the tools to process CRAMFS, it will further proceed to extract the CRAMFS into individual files. If it sees that there's a tar archive, it will further proceed to untar these files and so on. So Binwalk does a rather nice job. Let's see what we got in here. If we look at the CRAMFS root, this file system that you see in here is the uncompressed file system that is present in the IP camera. This is what you would possibly see on the RAM disk immediately when the kernel boots up. So what we're going to do is we're going to just take these, take this uncompressed file system and stick it into EMUX. We're now going to create a new virtual device and emulate it. First, before we do that, I'm going to give you a quick console tour of EMUX, and then I'm going to give you a step-by-step build your own device as well. So let me give you the console tour of EMUX first. The first thing you want to do in EMUX is you want to run launcher. A launcher will give you a menu. Some of these devices I've emulated, they're in my lab, so my list will always have a few more than the publicly distributed devices. But you should have, basically, you should have up to the first 6 devices present in the Git repo. All devices 7 onwards are like for my lab use internally. I use this for the training classes as well. Now let us pick up, let's pick up the which one shall we pick up? The IP camera, or we'll pick up the port control, the challenge. I will pick up the IP camera. I'm going to start the IP camera. So what happens is the kernel boots up first, and the user space does not automatically boot up. The kernel boots and waits for instructions from us. What do you want to do after the kernel is booted? So right now the kernel is booted and it is running a very minimal file system, a file system that I call as the host FS. You can't just boot the kernel and leave it hanging. You would have a file system to boot with it. Otherwise it will just not work. So it is running a host FS. It is also generated by build root, and it contains some basic tools and utilities which you can use for debugging. And when we want to invoke the userland side of the device, we will invoke another command called user space. And here's the user space command. And the user space command gives you 3 options. You want to drop into a debug shell, or you want to start the actual device. And we're going to say we want to start the actual device. Start the IP camera. And this will proceed to mount the extracted file system in a chroot environment and then kick everything off within the chroot environment. I'll explain you why we need the chroot environment in just a little bit. Now, the goal of EMUX was to create something as close as possible to an IoT VM, because it's easy to play with software. You want to test it, you want to debug it, you want to snapshot it, you want to load your tools in and out of it. Working with a virtual instance is very easy. You can't just say, okay, I'm going to copy GDB over to the IP camera. There's not enough space. You can't write to it. There's no persistence. So this makes it easy. And hopefully, Govind, Noan, and myself will work and put some fuzzing tools for the next level to be able to run some nice fuzzers on EMUX. Anyway, I get carried away. Let me start the IP camera. And what you're seeing here is all the boot up commands that are triggered by the scripts, the startup scripts. You'll see some errors on the console. And then eventually you will see like it's dropped into BusyBox shell, and it is running several services in the background. So all of these are the application services that are part of the IP camera. And eventually it is now steady stated. It's also giving us a prompt. If I do a PS to dump the processes, all these processes after EMUX init, all of these processes are part of the IP camera environment. So you've got your IP camera daemon, you've got the web server, you've got the OnVIF is the video streaming thingy going on, you've got the USB storage and Ethernet stuff and whatnot. So now let's see if this thing works, right? I'm going to open a browser. And because it's Docker, I can't reach the internal running instance directly. There's a port forwarder that I'm running in the EMUX environment, which will automatically forward certain ports. It'll publish these ports on Docker and then forward them to the QEMU that is running inside. Now, there's many layers going on inside. So simplifying this also took a little while. But the TLDR is if I now navigate to localhost to 20,080, this will get port forwarded to port 80, which is running on the emulated instance. And you will see the web interface of the IP camera pop up. There's a question, what was the command to kick off the user space in the second shell? I'm sorry, I went a little fast. Let me just paste the two commands. So first is EMUX Docker shell. And once you have the shell going, you just have user space. And if you want, just keep the emux.exploitlab.net web page open on the side. It's just following those instructions. But this is what I did. If I click on the camera settings, here is now I can actually play with this IP camera. I also found a format string bug using Burp Suite and fuzzing this. But there's a better bug in there, so I'm not using the format string exploit. But yes, at this point, you can do your web hacking stuff with it. You can fuzz it. You can reverse engineer it. You can even attach GDB to it and debug it. There's a cross-architecture GDB provided with EMUX, which makes debugging very easy. We'll see all that in just a little bit. But let me now give you a tour of EMUX, and then we'll start emulating the extracted firmware. In the meantime, folks, if you have got any questions, pop them up on Discord. And this is going to take a little moment on the side. Okay. Architecture diagram. It'll take a little while to get your head wrapped around the mess that is inside EMUX. So I drew 3 diagrams to see if I can demystify it. So the blue box is the Docker container that's running. Inside the Docker container, you have the EMUX directory, which I showed you earlier on. This EMUX directory is actually NFS mounted. Yes, NFS. I said NFS, good old Solaris, vulnerable as heck NFS. So NFS mounting the EMUX files from the volume Harambe. And there's a reason for the NFS mount. I'm using the volume because I want the data to persist. I don't want it to evaporate when the container ends. And the NFS mount allows me a beautiful property. I can modify the files from within Docker, And these files automatically become available inside QEMU. Because inside QEMU, the host FS that I'm running has NFS has an NFS mount command to pretty much mount the EMUX directory within. So I can share the root file system between the Docker container and the QEMU. You don't have to copy in and out. It's quite nice. This NFS is insecure as anything, like, yeah, read, write, root, bloody, whatever, everything goes. So don't be doing this in production. You're going to get owned so fast. But yeah, we're not going to let any security stand in the way of efficiency over here. Okay. Inside the QEMU environment. So once QEMU boots up, this Z image is the kernel. The host FS is the minimal file system that I compile using build root, which will mount the NFS directory EMUX. And then when you run user space, it will chroot the root file system and then kick off the processes inside of QEMU. The IP address of the device is always going to be hard-coded 192.168.100.2, and I can never figure out an easy way of making it user configurable, because so many things break and all these internal configurations break and so on. So hard-coded it is, and it's going to stay. It's quite a pain, but it's a pain that I'm willing to live with unless I find like a really elegant solution. I mean, some of you might be able to help me with that. Okay, now how does this QEMU that is running inside the Docker talk to the outside world? For this, there is SOCAT, which will forward ports. These are all user configurable by an environment variable. So by default, I've got port 80, 443, and 8080 forwarded. The external facing ports are 20,080, 20,443, and 28,080, and they get automatically forwarded to 8443 and 8080 inside the inside QEMU. And then there's this workspace directory, which is a bind mount between your host file system and the Docker. So quickly you can exchange files in and out. This is the overall organization of everything. So when you're browsing, you're doing a local host 20,080, it goes to SOCAT, gets forwarded to internal port 80, and that's how you get to see the web page. Inside the EMUX directory, this is the directory layout. There's quite a lot of things in there. I'll make it as simple as I possibly can in this time. All the blue boxes that you see down there, these are the emulated devices. Now, each of these emulated devices must have certain files in there. There must be a config file. There must be a rootfs file. Either you can keep the rootfs as compressed as tar.bz2, or you could keep the rootfs file as extracted already. If it's compressed, EMUX will automatically extract it when used for the first time. This is just for saving space on GitHub, no other reason. You need a kernel, which kernel that you want to boot up. And in certain ARM boards, you can also supply a NAND flash image using MTD parts, which is not going to be a part of this workshop. But sometimes supplying your own flash partitions is essential for, say, devices like the Tenda to boot up and run. And there's some NVRAM configuration parameters, which also we'll save for a later time, not now. But essentially, you have the same things repeated in all these devices, different kernels and different root file systems. The run directory contains all these scripts, the launcher and the parsers for the configs, the scripts that run chroot, and a whole lot of EMUX utilities or wrappers for easy debugging, dumping remote processes, process memory maps, killing remote processes, and stuff that you can do quickly on the command line without having to enter the running environment of the QEMU. And the host FS has basically three host file systems using build root. There's a host FS for ARM. There's a host FS for MIPS, and there's a host FS for MIPS Little Endian. Whenever I say MIPS, by default, it's MIPS Big Endian, and there's MIPS Little Endian. And there's a template if you want to create your new device, which is what we're going to use. And finally, once you've created your new device, you create an entry inside devices or devices extra. And then you get to also configure some finer points of QEMU configuration if you want. And this diagram, the last one. Now, all this is part of EMUX documentation. You have it on GitHub and you have it on the website. So I'm just just repeating these things here for you to map back when you look at it at a later date. These are 7 easy steps, 8 easy steps to emulate your devices. These should take you about 2 to 3 weeks to achieve. They're easy, but just take a lot of time. So you make a copy from the template. That's the first step. And then you get a compiled kernel. You compile a matching kernel for the device. You grab the root file system and throw it in there. If you want any NVRAM parameters, you throw them in NVRAM any. You want a flash, NAND flash emulated, you throw them in MTD parts. And if you want any library hooks to be injected using ND preload, you throw them in the preload directory. And lastly, you edit the config file, tie it all together, like the Lebowski rug, and then you add it in the device's database. And if everything works well, it'll work. So yes, let's now just do this. Like, enough of talk. And I'm going to shut off this once I've booted this IP camera. To shut it off, well, what you do is you have to get onto the Docker shell. So you need to do that, EMUX Docker shell, to shut down. Oops. Let me put the commands over here. And then I'm just going to do EMUX halt. So EMUX halt is going to start killing the processes, shuts the kernel down, and then exits the kernel. So this is now the device is shut down. Okay. And let's follow along with the steps. I sadly did not have enough time to prepare a good cheat sheet, but I'm going to type these commands in Discord as we go along. We're going to go to the EMUX directory and make a copy of the template into a folder called MyIPCam. Inside the MyIPCam directory. Now, don't worry if you can't follow along with this. The recording, once it's made available, it will have everything you need. So you can, if you feel you're falling back, don't stress. This is not going to evaporate. Inside the IPCam directory, you already have a config, you have kernel, you have preload, NVRAM, any MTD parts. We don't need the preload and MTD parts and all that. So I'm just going to get rid of MTD parts, NVRAM, And I'm going to get rid of preload. Just a second. Let's first choose the kernel. Now, in the kernel directory, I'm going to use a second shell for that, so you can keep them side by side. In the kernel directory, you have several kernels already available. We want this one, the ZImage2628 versatile no thumb. That is the closest kernel that matches the IP camera. How did I know this is the kernel? Well, when you look at the IP cam binary that binwalk extracted, if you dump the strings from the extracted kernel, it will tell you that this is kernel 2628. So I cross-compiled a kernel 2628 for the versatile ARM board. And then I'm using that cross-compiled kernel. So a number of cross-compiled kernels are also available with EMUX. If you don't get the exact one, you just try to fit the nearest one. Most of the time, it's going to work. If you need some custom stuff, then you have to go and compile your own kernel. I'm going to remove all the other kernels and just leave the ZImage2628 over here. I mean, you can leave them all there. It doesn't really matter, but I just don't like much clutter. Okay, so I've got it down to just the one kernel. And that's the kernel is done. Now for the file system. So for the file system, we're going to grab that extracted CRAMFS root. Right? We have in the temp directory, we have this CRAMFS root. We're going to grab that and place it in here. So just do a sudo move temp ipcam flash.bin extracted CRAMFS root and move it into this my ipcam directory. Make sure you use sudo. And I'm going to paste this command on the Discord. The next thing you want to do there is you also want to make sure the permissions are set. Right now it's all root, but I usually set the permissions to the R0 user. So everything can be edited by the same user. I'm going to make the modification here as well. Now we have these three things. We have the we have the kernel, we have the root file system, and now we need to edit the config file. Let me just first do a quick file. Let's list and see. So yes, we have the kernel, we have the CRAMFS root, and now we need to edit the config file. It's easy. I'm going to edit the config file very quickly. Let me edit it over here. You say, always add a comment. The ID must match the name of the directory. So if you called it my IPCam, this ID must match. We don't have NVRAM, so we can delete it. Our rootfs, the root file system directory is called CRAMFS root. So we're going to put this in CRAMFS root. The randomize VA spaces to turn ASLR on or off. We don't need any LD preload. This also goes away. And the init commands will simply use binsh for now. I'm going to save it. And this is my file. I'm going to place this also in Discord. This is the config file. We will now go and edit the main devices database file. Which is in the EMUX directory. I'll place this in here as well. I pasted the line to be added on Discord, and I will add it now for you. If you see, each of these lines represents one emulated device in EMUX. It starts with the device ID, then which QEMU binary you want to use, which QEMU board you want to use, any CPU subtype, the memory, the kernel, and these labels like vExpress2, Malta3, these are all essentially macros for further QEMU definitions, which I didn't want to muck with. And the last is the user-friendly name. I'm simply going to just paste this line right here, the same line that I pasted in Discord. I'm going to paste it right here. This is what we have added. Again, this ID must match the directory name and the ID in the config. That's how they look each other up. And yeah, let's see if this thing actually boots up. I'm going to save it. I'm going to run the launcher. And here in mine, I'm seeing in as ID number 7, I'm getting the ring 0 IPCam menu option. Well, let's click it. Let's push the button until it goes click. Starts the kernel. Drops you into the host FS. Now comes the fun part. This is the part where you usually spend 2 or 3 weeks on, is figuring out for the very first time, how do you emulate the correct sequence of scripts in the user space. This is where every device implements something quite differently. There's a bunch of spaghetti shell scripts floating around. So which goes first, which goes next? You have to literally spend a few days going over the file system that you extracted. Try to understand and try to trace from etc init tab all the way down to the other scripts. Reading through shell scripts is a mess. And unfortunately, there's no easy shortcut to following the sequence. You sometimes just have to keep doing it. You can use strace, ltrace, and a few other tracing techniques to make your job a little easier. But be prepared to spend about a week or two whenever you're working with a new device. That's kind of the norm over here. Okay, let's start the user space. Sorry, we got to do user space. So with user space, you get this menu. We're going to go start the Ring 0 2021 IP camera. Right now, it's doing nothing. It's just going to drop you into the BusyBox shell. You've not kicked off any services, nothing of the sort. But inside the BusyBox shell, you can take a tour of the file system. This is essentially the extracted file system that we're dealing with. All this stuff is what we grabbed from the firmware, from the chip itself. From this very chip, it's now over here. You can then walk around it, see the configs, like in etc, what do you have over here in etc? You have etc init tab. Usually etc init tab is the first thing that goes. And this file system is also available from the Docker environment inside CramFS root. So essentially what you're seeing on the top panel, which is running inside the QEMU, is the same thing that you're seeing in Docker. All this is being served across using NFS. So that's why it's like, if I need to make a modification, I can make it in the Docker environment, it automatically propagate inside the QEMU, thanks to NFS. So it makes life really, really easy. Now, if I look at etc init tab, this gives me a starting point, like what to do when init runs. So first command that apparently runs is etc init.drc sysinit, and then you have etc init.drc3. And then this is like just binds the console on the serial port, which we don't need to do. And everything else is for restarting and shutdown. So one by one, we're going to try and run these commands on the command line on our own and see how far we get. And usually the way to go here is you fake it till you make it. Keep trying. If something breaks, figure out what breaks, fix it, duct tape it, try again. It'll go a little further, it'll break again. Usually you like go further and further until it finally just runs on its own. That's when you know you have a big aha moment. It's a lot of fun. but this would take some time. So I'm just going to try init.drc.sysinit. I know it's going to fail because it is looking for a video device and the video device is not present. So it tries to mount the prop file system. It creates some devices and it cannot, it tries to look for a video device and it fails. It doesn't really go much further. What I ended up doing is I S-traced the whole process and figured out which video device was missing that this driver wants. And I faked it. This is like a cheat shortcut. The device in question is this one. It's a proprietary device, ABS 628. It's like the video chipset manufacturer, something Shenzhen 628. That's a company name. And this is a proprietary video device for which I don't have the hardware. And that's why the driver doesn't load. So what do I do with this device? I delete it. Now, this is where you just have to improvise. Like you don't know how to solve a problem. You just try everything. If you need inspiration and you get stuck, you pop up Kung Fu Panda and you watch that escape scene where Tai Lung, the snow leopard, escapes out of prison. That's how you do it. And then it'll work. I remove this and I touch ABS 628 to create a new empty file. I'm going to now try etc init.drc.sysinit. Now you see it proceeded further after this module. It went and created a few more and it popped open. It pushed that driver in. The driver, of course, is complaining, but it went ahead. The next thing I'm going to do is I'm going to now run etc init.drc3. And put these instructions on there. Okay. Now I'm going to run this etc init.drc3. Now, here we go. These various services are starting. Now, what you saw over here, right, this little glitch, it said ETH0 down, bringing it up again. This is like my cron job, my housekeeping cron job. If it detects changes to the Ethernet address or the link, it'll every 10 seconds, it'll try and reset the Ethernet interface to 192.168.100.2. Now, what happens here is that the factory default firmware of the IP camera is coded to a different address. When we extracted the firmware out of my IP camera, it will have my office's network address in there, like 10.20. something. So it binds the web services to, it tries to change the Ethernet address, and that's why it failed. But this script caught it and it brought it back up again. Let's see. If I now do PS, you will see that you see several things running. You see like HTTP client, web server is called webs, and it's good to go. If I do if config, it should show me that it is 192.168.100.2. So at this point, it seems that the IP camera is running. And I'm going to now show you in the browser how it looks like. Okay. So localhost 20,080. Yep, this is the IP camera. And I can go to like setting and TCP IP setup. Various things like this. So yeah, at this point, the device is emulated. It's working. It's also ready to be exploited as well. Like I'll show you how to debug this and how to then start using these. I use this for all vulnerability discovery and exploit development. So I'll show you what I can now do with it. Debugging this is easy, right? Now let me show you some of the ARM, the EMUX commands. Like you have EMUX PS. EMUX PS will remotely dump processes on the target, whatever is being emulated. And then you have EMUX netstat, which will show you the listening ports on the target. This word's all listening. You can also dump the process memory maps of any process. Like we want to dump the memory maps for. Hey, hang on a moment. Just a second. Right. So let me dump the process memory maps of this web server. I'm going to say EMUX maps. You just name the process webs, or you can give the PID as well. And this will show you all the virtual memory map layout of the target web server process. This is an ARM binary. If I want to debug it, all I have to say is EMUX GDB and the webs process. Here's the debugger going. And it's attached to the web server process. If you've used a GDB and GEF, this is all familiar territory. And let me see if I can very quickly. Do I have an exploit at hand? Maybe. Okay. So I have a very quick exploit script over here. Essentially, this script just dumps a bunch of A's in the URL part of the URL string. Now, this is what I use to do, use EMUX for exploit development with. So I do this, pipe it to netcat, 480. And you'd see in GDB, you'd see the crash occur. You'd see the crash, you get a segmentation fault, you get all your registers, you get a program counter. And this is like, this is the beginnings of a Stack Overflow. So anyway, I was kind of got carried away because the demo worked really well. I was very happy. So I showed you all these things. This is what EMUX does. It's this is like the whole framework and the tools, stuff that I use on a daily basis for all my production work. I know there's a few questions on Discord. Someone saying is not able to run etc.init.drc3. Well, we'll have to figure out what the scene is. I'm going to keep the Discord channel open. Have at it. I'll also respond once the workshop's done. We can play around. I'm not just going to abandon you and run away. We'll get to that. We'll get to seeing what this is. But this is like a classic situation, right? Once you encounter such an error and nobody knows, right? You're the first one to emulate the devices. Then the best debugging tool, I'm told, is you get yourself a little debug ducky. Here is my debug duck. Duck's amazing. So what you do is you describe the problem in great detail to the duck. All the detail that you have, talk to it twice. And by the time you finish talking a second time, the duck will have an answer for you. It's telepathic. Trust me on it. So yeah, that's what you got to do. All right, let me wrap up the concluding slides. There are a few important things to say about EMUX, and then we'll open up to question and answers. So again, back to the documentation. This is what the whole process of how EMUX starts. What happens when you start the launcher? What happens when you start the kernel? What happens when you start the user space? So this is typically the flow. Goodies are always going to be on the repository, and watch for some announcements on my Twitter feed. I keep posting updates to the repository. If there's like something significantly new about EMUX, I'll post. This was the first official release of EMUX. I'm going to tweet about it in the documentation. So far, it's just been shared privately with friends and now you folks. It would be amiss if I did not mention the efforts of my two very good friends, Guven and Noah, over here on the panel, for brainstorming EMUX and testing EMUX and a non-stop series of Big Lebowski puns as well, which is very essential when you want to develop frameworks. So before I wind up, let's take a few questions. Let's take any issues that you may have on Discord. I see this RC3 issue. I can possibly take a look at it, like with. Oh yes, I forgot to mention there is a log in EMUX as well, which the log feature might come in handy for you. The logging allows you to. It's nothing but just dumps all the console output. But let me show you how it is. So by default, logging is enabled. If you go to the EMUX root directory, there's a file called debug logs. Now debug logs will drop logs at a specified path. So for me, they're dropped in workspace logs directory. You can comment it and customize it. I like to drop it in workspace so it's available on the host as well. Now in the workspace, if you go to logs, you'll see two files. There's an EMUX debug log and a QEMU console log. These will just give you some of the like if you're adding in QEMU and the command is failing, this gives you how the QEMU debug, the device's file is parsed. It'll tell you what the output on the console is. Anything that might help you in troubleshooting that. So the log feature is there. Few more questions. Are there plans to add support for Qualcomm-based Wi-Fi hotspots, and which QEMU version are you supporting EMUX? Now, Wi-Fi firmware is a super tricky issue. It's Ralph Philip Weinman and his bunch of merry men did a project called Lua QEMU a few years ago. Brilliant piece of work. Ralph Philip is a bloody smart guy. So they emulated I think they emulated the Broadcom Wi-Fi firmware in Lua QEMU. So Lua QEMU is nothing but a QEMU with a lot of Lua hooks, and you essentially just write traps when a memory address is accessed, and you fake the whole Wi-Fi driver with it. I am not in that league. I'm nowhere near that level of Lua smartness. So yes, I will. I doubt I'm going to be able to add this type of hardware support. Hardware has always been a challenge. Which QEMU versions am I supporting in EMUX? Essentially, any QEMU that you can compile and drop in. Let me show you. So in EMUX, in EMUX run, there's a QEMU bin file, and I have QEMU system ARM and MIPS version 6.0 and 6.1. You can drop your own in there. So tomorrow you want to do this for PowerPC, all you got to do is like just drop a QEMU system PowerPC in here, and you can extend this to PowerPC. Okay, so not just talking about the Bluetooth modem part of the Qualcomm, just the web and network part. Okay, hey, yeah, if you want to assist, my friend, yeah, absolutely, go for it. You want commit drive, you want like contrib drives or something, happy to have you on board. That would be an absolute pleasure. Yeah, so far it's all limited to 32 bits, but I do not see why we can't go to 64 bits. We can easily do like QEMU system ARX64 and build a build root host FS for 64 bits, not difficult at all. And then just 64 bits kernel. So that is possible, not a problem. Have you encountered an IoT with two different processors, one that starts the other processor? How would you debug that? No, I have not. There are baseband processors, like you have a Cortex R or a Cortex M, which have bare metal firmware on there. So I'm not familiar with those. No, not at all. I don't know how to pull that off. And thanks for the ARX64, the ZTE stuff. Yeah. These are super awesome stuff. Like definitely, it would be great to have your your experience. I mean, yeah, EMUX is open source, so I welcome any and every contribution, and hopefully this project just grows and becomes much larger than just these things. You're most welcome, folks. Okay, some more questions coming in. Will you be doing an online version of the ARM IoT Exploit Lab very soon for those unable to attend offensive? I know I have something better. My next training is going to be in August. We are doing Ring Zero unofficially. We are going to go back to Vegas. Let's just hope, right? Let's just hope things continue progressing in a healthier manner. By August, hopefully things would have cleared out one way or the other. In August, I want to do two courses. We are going to do Ring Zero in person, and the following week will be virtual. The classes that are taught in person will not be taught virtually, and vice versa. The classes taught virtually are not taught in person, but it'll be a 2-week event. It will, I want to feature a MIPS class and an ARM class in the August event. So that's what my plan is. For the near term, I am not teaching this at Catch 2022, but I might do another workshop in March or something. So my next class will be in August. Well, so folks, this is the last of the this is the last part of my workshop. Hope you folks had a good time. I really did. I was a little nervous up front if the demos didn't work, but the demo gods helped me, and I'm sure Harambe is looking down upon us as well with great love and joy. All right, I'm done. Thank you, folks, very much. Thank you for your time, and thank you for your attention, and thank you for sparing your Sunday with us.